But if you need the absolute highest accuracy, then you will have to go with the sensor technology from the optical group. My name is Lian, I'm a sensor specialist, and in today's video you will learn how to select the right distance sensor for your application. In the first part of this video you will learn what distance sensors are and what they can be used for. In the second part I will show you how I would go about selecting the right distance sensor for my application on the example of the Micro-Epsilon distance sensors. And in the third part we will wrap everything up with some real-life application examples. So what are distance sensors? That's actually very simple. A distance sensor is a device that measures how far away an object is from the sensor. Note that a distance sensor is not the same as a proximity sensor, since a proximity sensor will only tell you if some object is within its range, but it will not tell you how far away it is. Now, by measuring the distance, we can measure the length of an object, the displacement, and the position. As you know from physics class, we can additionally derive the velocity and the acceleration from the displacement of an object over time. We can also measure the vibration, or more specifically the frequency of a movement and its amplitude. If we use this type of sensor to measure the deflection of an object, we are even able to calculate the force that is acting onto that object. By putting a distance sensor on a 2-axis stage, we can generate 3D profiles of an object and also measure the surface roughness. And if we mount two sensors in a way that they are opposing each other, we can measure the thickness of an object. Some distance sensors even allow us to measure the thickness of an object from a single side. And I could go on with these examples. So you see, as simple as a distance sensor sounds, it is an extremely versatile device which definitely deserves recognition. Now, with distance sensors being used in so many different applications, there exist a lot of different types of distance sensors which are based on different measuring principles. If you don't deal with sensors on a daily basis, this makes it quite time consuming to figure out which sensor is the best one for your application. Therefore, I will now give you a rough guide on how to select a distance sensor. And again, I will do this on the example with the Micro-Epsilon distance sensors. Before we start, if this video was helpful so far and you want to stay updated on sensor technology, then subscribe to the channel and also to the newsletter. You're most likely eligible for a free consultation, so check out the video description below for more information on that. Now let's start. From my experience, there are 3 distinctions that will help you to greatly narrow down the relevant sensor technologies for your application. The first and easiest one is contact versus non-contact. With contact-based solution, some part of the sensor is either touching the target or directly attached to the target. This has the advantage that you can measure on almost any type of material. So for contact-based sensors, it's usually not relevant whether your target is made of wood, polymer, metal, or some other type of material. You only need to be in contact with the target. Additionally, a lot of contact-based sensors can be used in harsh environments, and they are typically more cost-efficient than the non-contact sensors. Since non-contact sensors work with some sort of waves, for example light waves or electromagnetic waves, a single non-contact sensor technology usually cannot measure on all types of materials, but their measuring principles have a lot of other advantages. The sensor won't have any mechanical wear. The space between the sensor and the target is free. Since the sensor doesn't touch the target, it won't influence the measurement. You also don't have to worry about scratches and other damages. Without the mechanical connection, higher frequencies are possible, as we don't have to overcome any inertia and are not limited by any spring frequency, for example. And in general, non-contact sensors are usually also more accurate. Due to all these advantages, they are often used in high-tech industries like the semiconductor industry, and this industry has pushed the development of vacuum-compatible sensors forward. So vacuum compatibility is another advantage here. By the way, even if a non-contact sensor is not vacuum compatible, you can take advantage of the fact that waves can go through glass. So if you have a chamber with a glass window, then you will be able to measure through the glass with at least some of the non-contact sensors. After deciding between a contact and non-contact system, our next criteria is the measuring range of the sensor. I will classify everything above 500 mm as long range, everything from 500 mm to 30 mm as mid-range, and then everything below 30 mm as short range. And of course, these thresholds are only a rough guideline, but you can see that they already separate the sensors quite well. Now, the measuring range is typically defined by your application, so there is usually not much you can do about it. However, I want to note two things here. The first one is that there is a correlation between the measuring range and the accuracy. A larger measuring range will typically decrease your accuracy. Therefore, don't go with a larger measuring range if you don't have to. Keep it as small as possible. The other thing you should know is the difference between an offset and the measuring range. The offset is basically the start of the measuring range. So if you, for example, need a sensor that should measure the distance to an object which is 500 to 550 millimeters away from the sensor, then you really only need a 50 millimeter measuring range with a 500 millimeter offset, because no action is happening in the 0 to 500 millimeter range. With such a sensor, you would typically achieve a way better accuracy compared to one with a 50 millimeter offset and a 500 millimeter measuring range. Of course, you might not always find a sensor with your desired offset, but you should rather go for a larger offset than for a larger measuring range. After deciding between contact and non-contact sensors and selecting a measuring range, you can see that you already narrowed down your choices quite well. However, for the non-contact short range category, we still have quite a few options. And this brings me to the third decision criteria. For the third decision criteria, we won't look at a single specific sensor characteristic, but we will rather group the sensors into electromagnetic sensors and into optical sensors. The reason for doing that is that within such a group, the sensors have some very similar characteristics. The electromagnetic sensors, for example, can only measure on conductive target materials. The optical sensors, on the other hand, don't depend on the target material, but rather on the optical characteristics of the top surface of that target. Next up is the target size and the measuring spot diameter. The electromagnetic sensors typically have a spot size of at least a few millimeters, while the optical sensors can have spot sizes in the micron range. So if you don't want your measurement to be influenced by the microscopic surface structure of your target, then you'd go with an electromagnetic sensor. But if you want to measure microscopic details, then you need an optical sensor. Then let's look at the offset. The electromagnetic sensors have either no offset or almost no offset. This makes them ideal if you have space constraints. And by the way, the electromagnetic sensors can also be extremely tiny and lightweight. The optical sensors can have offsets of even more than 100 millimeters, for example. This can help you in situations where you need a bit more clearance to the part because maybe your positioning system has a higher tolerance, for example. Then we should also look at the temperature. While the high temperature versions of the electromagnetic sensors allow you to get very close to hot targets, the optical sensors are often limited to a maximum of 70 degrees Celsius. But keep in mind that the high offset of some of the optical sensors allows you to position them further away from the target, and that might make optical sensors feasible even though the target temperature is way above 70 degrees Celsius. And finally, let's look at the robustness of the two groups. The electromagnetic sensors are usually way more robust than the optical sensors. The eddy current sensor, for example, can be used in dirty, oily, and moist environments, which is definitely not true for the optical sensors. By the way, the electromagnetic sensors on average also have a better price to accuracy ratio, but if you need the absolute highest accuracy, then you will have to go with the sensor technology from the optical group. Now, to sum all of this up and get a small exercise out of it, we will look at three very different examples. In the first one, let's say we're manufacturing trucks and want to measure the displacement of its outriggers. In this case, our target is not fragile, and to keep everything cost efficient, we therefore go with a contact-based solution. Since the movement is typically more than 500 millimeters, we need a long-range measuring system, and therefore the draw wire sensor would be a good choice here. In the second example, we want to measure the ground clearance of a race car. In that case, we definitely need a non-contact system, and since the suspension will have a travel in the mid-range, we can go with the laser triangulation sensor. And in the last example, we want to measure the distance to a silicon wafer on an air bearing. Here we again need a non-contact system, and since we might want a bit of standoff from the expensive wafer, we should go with an optical solution. For such a specular target as a wafer, the confocal and interferometer technologies are ideal, so now it really depends on what accuracy is needed. So I hope that this video gives you a rough idea of what kind of distance sensor might work for your application. When selecting a distance sensor, make sure that you know all your requirements and ideally talk to your sensor specialist before purchasing a system, because there are always some things you have to consider for each technology. If you don't have a sensor specialist on your side yet, then check out the video description below, as you're most likely eligible for a free consultation. Thanks for watching and good luck with your measurements.